Hi everyone, my name is Willy Kwon. I'm a technical leader of computer vision and image signal processing part at Chips&Media. Before we start our Q&A session, let's talk about why dedicated deep learning accelerator is recommended to use for super resolution in real-time application. The super resolution, which is called SR, is the image scaling algorithm that upscales a low resolution image to high resolution. There are multiple ways to perform upscaling, for example, conventional scalar and super resolution. The conventional scalar is based on the frequency filter, and it manipulates only existing frequency components. Therefore, there is a limitation to recover high frequency patterns. However, the super resolution uses the implicit visual dictionary to map a low resolution patch to high resolution. Therefore, it produces realistic high frequency patterns. The super resolution has outperformed all the previous methods with tremendous attempts by adopting deep learning neural network in recent years. There are two main approaches to implement the neural network-based SR. One is NPU, Neural Processing Unit, and the other is dedicated deep learning accelerator. Let's find out what the differences between NPU and dedicated deep learning accelerator are. First, NPU is a processing unit of the neural network like GPU for graphic processing. It is architected based on the instruction and is programmable. Therefore, it supports all kinds of neural networks theoretically and can be updated using the latest network even after the manufacturing of the chip process is completed. But it is not easy to implement better network in NPU since there are limitations of NPU performance in real time. On the other hand, a dedicated deep learning accelerator is a network-specific hardware accelerator that's fully hardwired and supports one specific neural network. So it achieves high performance, low power consumption, and virtually zero DRAM bandwidth at the cost of generality. In high resolution application, the only dedicated accelerator can meet real-time performance, such as the 8K 60 frames per second display or camera. Let's talk about the challenges for NPU when implementing the neural network-based SR. When implementing SRs through NPU supporting 4K or 8K 60 frames per second in real time, there are many obstacles to solve, and bandwidth, for example, is one of them. As shown in this image, NPU is composed of general hardware, and the various networks can be implemented in this hardware by using the instructions. Since each layer's result value is used as the input value of the next layer, so a massive DRAM bandwidth is used. This table shows the DRAM bandwidth of NPU and dedicated accelerator when the SR network is used to generate 8K 60 frames per second. The image quality improves by order of SR-CNN, VDSR, and EDSR. Remember, the better the image quality network it is, the more exponential bandwidth in NPU. For example, FSR-CNN is known as a cost-effective network and is widely used for real-time SR. Even FSR-CNN implemented on NPU also consumes extreme bandwidth and power consumption that the system cannot handle. So dedicated deep learning accelerator is a smarter choice than NPU over for real-time SR. Okay, we now know dedicated deep learning accelerator is a better choice when implementing high-resolution real-time SR. Well then, what are the most important aspects when implementing dedicated deep learning accelerator? Let's find out. Take a look at the graph. It shows the distribution of PSNR and GMAC for 8K resolution in popular SR networks. Please note that the x-axis is the log scale. For example, the GMAC of VDSR is about 200 times bigger than the one of FSR-CNN. We can see from the graph that the network from the most recent papers are distributed in the red circle. Each network shows outstanding image quality, but the gate size is unimplementable in a real chip. For example, the estimated gate size of EDSR is over 50 billion gates. See the implementable network in the green circle. The gate size is acceptable, but shows poor image quality. That's why it is very important to choose the proper network selectively. Here is what we've accomplished. C-Wave 120 is the SR network that we have developed solely by experimenting with the CNN proprietary theory to achieve better image quality and less gate count. It shows a less gate count than implementable networks and has comparable image quality as recent papers. For example, it has a similar image quality as the VDSR, but is 1,000 times lighter. Here is our C-Wave 120 specification. Our C-Wave 120, a neural network deep learning-based super resolution hardware IP, supporting 8K resolution 60 frames per second at 550 MHz. Supported input image formats are YV400, 420, and 422, with a bit width of 8, 10, or 12 bit. There are two operation modes you can choose from: M2M to reduce the internal memory size, and on the fly to reduce bandwidth. It is supporting frame compression and non-frame compression format for the input and output pixel data of C-Wave 120, with arbitrary scaling ratio between 1 and 8. Here, compare how different these two images. The left is upscaled by conventional scaler, and right is upscaled by our C-Wave 120. If you look at the highlighted box, we'll notice the object looks clearer and focused on the right. Image quality is also very important for low resolution images. This picture is captured from YouTube. Again, the image on the left is upscaled by conventional scaler, and right is upscaled by C-Wave 120. By just looking, you'll notice the image quality improvement with less codec noise. Before we move on to Q&A session, I'd like to share the news that we are currently expanding our super resolution hardware IP portfolio to provide more computable SR hardware IPs with different power, performance, and size. So stay tuned and reach out to us if interested. Thank you everyone for listening, and let's begin our Q&A session.